Morning, folks. You doing okay? Listen, I don't have your exam this morning. I will have your grades up today, and I'm very sorry. I know that y'all are eager to get your grade. Shoot. Give me just a second, guys. I'll be right back. Grab that. So anyway, I'll have your grades up this afternoon on Moodle, or yeah, by this afternoon. Hopefully this morning I'll have them up, but definitely by this afternoon. I don't know, the exams are looking okay. They're sort of as I expected. It was a tough exam. Some of you obviously knew exactly what you were doing, and some of you sort of knew what you were doing, and then some of you were not really so sure. So I've been trying to be very generous with partial credit. So if you had something written down that was right, I try to give credit for that. But yeah. Anyway, I'll have them up soon. If you want to drop by this afternoon, I can after I post the grades, you can pick up your exam, or I'll hand them back on Monday. Um, if you are thinking about dropping the class, then please don't do so right now. Just come talk to me first. There is another exam before the drop day, so I would recommend not doing that. You have to have the class anyway, so if you're thinking about dropping, just sort of stick with it until the end of the third exam, and then you'll have a better idea sort of where you are. And I often find that students sort of think the situation is a lot worse than it really is, because there are a lot of points in this class, and there are what 600 or so points, and we're not even halfway. So just hang in there. There's still a lot left to do. All right. Y'all feel okay today? It's been a tough week, right? Has it been tough? I think y'all had organic exam. Is that right? Some of you had organic, micro maybe. Some of you had micro or whatever. Huh? But y'all take biology too, don't you? Yeah. Okay. All right. Any big things going on this weekend? Of course, it's homecoming, right? Y'all going to the game, tailgating, yada yada yada. Yeah. Okay. Anything else going on this weekend? We might try to make it out to the game. Should be fun. Um, no? All right. Well, let's get started on chapter 5. And the good news is that I feel like we're sort of over the hump. Like that chapter 4 and chapter 3 lumped together, that's just a really tough exam, and students often have a lot of difficulty with it. But chapter 5 and even chapter 6 are pretty straightforward. We're going to see a little bit of new calculus in chapter 5. We'll see the dot product, which some of you have probably never seen. You won't see it till Calc 3, I think. It's a vector product, or a scalar product rather, but a product of two vectors. Um, but it's really easy. I'm going to show you. It takes like 5 minutes. You'll master it. It's like nothing. It's easy, super easy. And we'll look at work and energy. If you've had physics before, you've almost certainly done this, doing work on objects, and then also the conservation of energy. We'll see a little bit of work with integrals in this chapter as well, where we're calculating the total work that's due to a force that's variable with distance. So integrating over a force as it acts over a certain distance. Um, but otherwise, it's a pretty straightforward chapter. I think that maybe not easy is the right word, but it's easier than the previous chapters. It's less complicated. We'll also see less building on previous chapters. We'll see a little bit of stuff that we did in previous chapters, but not as much as we did before in chapters 3 and 4. You follow what I'm saying? Chapters 3 and 4 very much built on chapters 1 and 2, but we're going to move away from that. Likewise for chapter 6, but then in chapter 7, we're going to sort of revisit everything. And chapter 7 will be a sort of another littler hump than we had for chapter 4, but a hump nonetheless. Okay? One other thing, we will have an extra credit opportunity. Uh, every semester for this class, we have to do a general education assessment. and I'm gonna use that this year for extra credit. Uh, I'll let y'all know. It'll probably be next week, towards the end of next week, but I'll give you a good little heads up and let you know exactly what will be on that assessment, like what topics will be covered. But it'll probably be chapters 1 through 4. I haven't written it yet. I'm actually revamping it from what we've had from previous semesters. But I think that you'll find the questions, I'm not supposed to use straightforward. I think that you'll find them simpler than the questions that we had on the chapter 4 test, the chapter 3-4 test that we just had. Okay, but more about that soon. It'll be about 20 multiple choice questions, and the percentage that you get on that will go towards extra credit in the class. So if you get 100%, you'll get 20 points. If you get 50%, you'll get 10 points. You follow me on that? It's a new way. I've never done this before, so I think it'll work well. I want y'all to really make an effort on the assessment. That's why I'm making it for extra credit, but I don't want it to hurt you if you don't do well on it. Okay? Does that sound good to y'all? You should smile, right? That's a good news, I think. 20 points. It's not a whole lot of points in the class. It's almost 3 percentage points, I think. But, you know, that's 3 percentage points. That means that it will affect a third of you. If all of you get it, it'll affect a third of you uh, in increasing your grade from one letter grade to another. That's a pretty big step, actually. Okay? Let's see. Let's start with energy. We have lots of different kinds of energy. Uh, we'll discuss in this chapter two types of energy, that associated with motion, or that associated with the potential for motion. My notes out here. David? What are you doing? The type that's associated with motion, we call kinetic energy. Usually for a variable for this, I'll use the KE. Sometimes in other books, you just see K for kinetic energy. We'll also discuss the energy associated with the potential for motion. This is called potential energy. And potential energy, we'll use the variable PE. We'll have several different types of potential energy. Actually, we'll only use two different types of potential energy: elastic potential energy, like in a spring, and gravitational potential energy. This just says that an object, if you have it at a certain position, then it has the potential for motion. So, good example of that, if I have an object and I hold it up here, this object now has the potential for motion. All I have to do is just let it all I have to do is let it go and it moves. Likewise with a spring, if I have a spring and I compress it, it now has the potential for motion. If I let it go, then it will move. So we use PE. Often people in other books you might see also the letter U for potential motion. Yes. All right, so collectively these are called mechanical energy. This is in contrast to other types of energy, thermal energy. Your chemistry majors one semester of your PChem class. You have 2 semesters of PChem, and you can sort of think of those, one of them as being quantum physics and the other as being thermal physics. So you'll spend a whole semester just dealing with thermal energy and thermal physics, and you'll deal with it actually collectively. So I don't know if Dr. Lowe, anybody had PChem? No, y'all can't have had PChem yet. But I think Dr. Lowe does like a classical development of thermal physics where he uses the concept of energy and momentum to develop these expressions for how to describe the thermal energy of a gas. Anyway, so you'll see that again in a whole semester. It's kind of a fun class. Actually, no, I don't think it's really that much fun. Like it was probably we had to take a physics class on thermal energy, and it was probably one of the more difficult classes, and it never really clicked with me. But I know that it clicked for some students, and hopefully that'll be the case for you. It will click for you, right? Chem majors. It's a fun class, though. I think you'll like it. So anyway, this is in contrast to thermal, nuclear, electrical energy. Uh, we'll talk about electrical energy next semester. We won't get to thermal or nuclear in this class. Um, so let's do the dot product just sort of as a little aside. Again, this is Calc 3, so you won't get to it. Well, no, y'all take Calc 3, right? Chem majors take Calc 3. You go past Calculus 3? You stop there? Right, okay. Anyway, you'll get to this in Calculus 3, but it's real simple. The dot product, this is also called the scalar product. It's just the product of one vector, or rather, I'm sorry, of the magnitude of one vector with a component of a second vector, and the component of the second vector is in the same direction as the first vector. So basically, I want to take two vectors, and I want to multiply two components of those vectors that are in the same direction. So graphically, that would look like this. If I had vectors A and B, my vector A is in this direction. My vector B is in this direction, but the x component of the vector B is in that direction. And what I'm doing is just multiplying the magnitudes of those two vectors. So it's a mathematical tool that allows you to do this, to take two vectors, multiply one vector times the magnitude of the other vector that's in the same direction as the first vector. So I'm just multiplying the vector A times this x component of the vector B. Or it doesn't have to be x component, it can be the y component, but it would look like this. So if I was to draw my vector A like this, and then my vector B like this. It's my angle theta. This would be B. This would be B cosine theta. So it's not necessarily the x component. It's just the component of the vector that's in the same direction as the first vector. So this is how we draw the dot product, or how we express it. And it's just equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And I think that's apparent. Is that apparent from the previous figure? You're just taking that x component of the second vector. So I have my first vector, and I'm just multiplying it times this component. And this component, whether it's in the horizontal or in the vertical direction, is always going to have this cosine theta term. So my a times b cosine theta, this will always be cosine theta. Sometimes you'll see these vectors written a little bit differently. So I might have a vector A and I might have a vector B like this, and they're separated by an angle theta. Still it's going to be A, B cosine theta in taking that dot product. Okay, so this is just a tool. It's a mathematical tool that allows you to take two vectors, multiply the component of one times the component of another that are both in the same direction. And that tool we'll use when we're calculating work, because that's something that we'll want to do, to take the first vector and multiply it times the component of the second vector that's parallel. All right, so this is how we determine the dot product. When the vectors are in vector notation, we just multiply out the components of the vector. So, for example, if I have two x components of vectors, and I want to determine I dot I just do 1 times the cosine of 0. So I dot I would be equal to 1, whereas I dot j, these are two vectors that are perpendicular to one another, I and j. So this is my I vector, this is my j vector. The x component of the j vector, by definition, doesn't exist, right? Because the j vector is a unit vector in the what direction? X, y, or z? In the y direction, right? So this jx doesn't exist, so the dot product of these two vectors would be 0 because they're perpendicular to one another. They can't be in the same direction. There is no component of j that's in the same direction as I. All right, so these are the only three dot products, I, J dot J, and K, that are equal to 1. All the other combinations are equal to 0. So I dot J, I dot K, uh, and J dot K, I guess, is the only other. Okay, let's see. You'll find that this, you might sort of catch on this, but we'll do vector products later. Next chapter, I think. No, in a couple of chapters we'll do vector products, and they're very similar, or they're a little bit similar to dot products, but this is not true for those. Uh, I'll see that A dot B is equal to B dot A. I'll sort of list that as an aside. It's not terribly important right now, but when we get to cross products in a few chapters, it will be important because that's not true for cross products. What's this called? Is this the commutative property? Is that commutative? Yeah, so it's same as true for numbers, right? That 2 times 3 is the same as 3 times 2. Okay, so let's say I have these two vectors, 2I plus 3j, and 1I minus 2k, and I just want to find out what is the dot product. So I just write out my vectors. I want to know A dot B. That's equal to 2I plus 3j, and then I dot it. I take the dot product with 1I minus 2k. So what you're going to do here is just use FOIL, the first outer inner last thing to expand this. And then you know that these things are true, that I dot I is equal to 1, I dot J is equal to 0. And when you expand that, then you'll see that some terms go away. So for example here, my first term, the first, would be this times this. That's going to be 2 times 1 times I dot I. 2 times 1 times I dot I. And then I can do the same for the outer, the inner, and the last. So just, amuse me and go ahead and write out the full expansion of this, the first, outer, inner, last. And then you'll see that some of the terms will go away. So go ahead and expand this out to its full form. See, I did first already. I'm going to do outer. Inner. And last. All right. So if I want to know the dot product, I see that several, or one or more of these terms goes away. Which ones go away? First of all, I dot I, 1 or 0. That's 1. I dot K, 0. J dot I, 0. J dot K. Yeah, there was this 3J and 2K. So I have a J dot K here. That's equal to 0. So these last three terms, they all go to 0. I dot I is equal to 1. So my dot product here, these all go away. My dot product is just 2 times 1 times 1. It has a value equal to 2. Note that this is not a vector quantity. In fact, that's why we call it a scalar product. The dot product is also called the scalar product. The result of a dot product is a scalar quantity. Um, and then also I've said this, but the dot product of orthogonal vectors or perpendicular vectors is always equal to 0. So if I do a 2I dotted with 3j, that's equal to 0. Or if I do a 3j dotted with the vector 2I plus 4k, those two vectors are also orthogonal. I have a vector in the y direction. See if I can draw this. I have a vector 3j in this direction, and then I have a vector 2I plus 4k. That would be like in this direction. These two vectors are orthogonal, so that dot product would also be 0. Okay? So that's dot products. We'll practice with the dot product, but you'll certainly see it on the next exam because you'll have to calculate the work done by a force, and I'll give you the force in vector quantities with unit vectors, I mean. So more to see there, but it's just a tool. It's just a tool that allows you to take two vectors and multiply the first vector times the component of the second vector that's in the same direction as the first vector. And we use it to calculate work. We use it for a bunch of things, but in particular, we use it to calculate work. So work is done when a force is applied over some distance. And to calculate the work, we must multiply the magnitude of the force times the component of the displacement that component which is in the same direction as the force. Okay, so you should read this and you should think to yourself, this is my dot product. And in fact it is. That's, I said, one of the purposes that we use the dot product for is to calculate this work. Um, so we define our work then as F dot D. That's the definition of our work. Based on the definition of our dot product, it's also F times D times the cosine of the angle theta. Okay. By the way, let's just do a quick little aside. Let me show you something. Let's say that I have a vector. Let's say that it's 2I, and I want to dot it with another vector, 3I plus 4j. Okay, so I can find the magnitudes of these, or I could find the dot product. The dot product would just be equal to, y'all know what the dot product that is right off? It's going to be equal to 6, because I really just multiply these two terms, and I don't worry about the j term. It just goes away. And in fact, when you're writing out your dot product, you don't need to fully expand the whole FOIL business. You can just go through and say, well, that's 0, that's 0, that's 0, and that's equal to 1. So when, on this previous dot product that we did here, I don't really need to write it out all like this because I can just look and say, well, these two terms do multiply, these do not, and these do not because they have perpendicular unit vectors. But let's say I have these 2I times 3I plus 4j. Um, this would be the difficult way to find it. I mean, the easy way is just say 2 times 3. But I could say, well, this is equal to f, or let's say that this is our f and this is our d. This is equal to f times d times the cosine of the angle between them. So f would be 2. D would equal to the square root of 3 squared plus 4 squared. Right, that's just the magnitude of that second vector. And then I can find the angle theta here. The angle theta of this vector would be the inverse tan of 4 over 3. The inverse tan of 4 over 3, I get to be 53 degrees. So I do cosine of 53 degrees. And this should give me the same answer as just this simple way of dealing with the unit vectors. So I say 2 times, what's that, 9 plus 16 is 25. So that's 10 cosine of 53, which is equal to 6. So sometimes you'll have vectors where you'll have, say, the force and the displacement in unit vector notation, and then the easiest way is just to do the dot product. But sometimes you'll just have the magnitude of the force, and then maybe the magnitude and direction of the displacement, in which case you'll do this. Okay, either way is correct. In fact, if you have it this way, you can go through and calculate it this way, but it's a lot of steps that you don't really need to take. So you'll see both of those as we work through some problems. All right, so here I have the force. This is my force right here on this object, and the object is moving in this direction. So what I want to do here is take the component of this force that is in the same direction as the displacement, and I'll just take the product of them. So in this case, our work done by this force is going to be F cosine theta times my displacement, which is delta x, which goes back to our definition of work, FD cosine theta, or more importantly, our definition of the dot product, which is FD cosine theta. All right. Now, when the two are parallel, it becomes a lot simpler. So if F and D are parallel, that means that we have FD times the cosine theta. If they're parallel, what is theta equal to? Uh, 0. Yeah, cosine, this is equal to 0 degrees, but the cosine of 0, probably what you meant actually, right, is equal to 1. So when the two are parallel, our work is just equal to the force times the displacement. Okay? The unit for work is the joule. It has these basic SI units. 1 kilogram meter squared per second squared, is that right? A newton meter. A newton is a kilogram meter per second squared. And then I'm just adding in another meter there. So it's kilogram meter squared per second squared. Uh, some people actually, you'll see this in a lot of textbooks, that they'll use the units for work to be 1 Newton meter. Notice that these are the same here, but I'm going to use joule for work just so that we can draw the analogy between energy and work. Because we'll see that energy and work are both very closely entwined. So I'll use joules, which is a measurement of energy, instead of Newton meters. But if you see this in other textbooks, you might see Newton meter instead. But I'm going to use joules because joules is typically the unit that we use for energy. And energy and work are just very closely related. We'll see that later in this chapter. Also not going to use Newton meters because we'll see that again when we talk about torques. You might have seen this. Like, you ever use a torque wrench? Torque wrench has foot-pounds, or sometimes it'll have Newton meters. That's not a measure of work. That's a measure of torque. It's same units, but a different quantity, a different physical quantity. So not going to use Newton meters, but a lot of textbooks do that. So just want to point it out to you in case you see this. And for you engineering students, you might see work as Newton meters in the future in some of your higher level classes. Yeah, probably will. Okay. See, if there's no displacement in the direction of the force, there is no work done by the force. So we see this a lot, right? Like right now, there are all sorts of forces acting on you, but there's no displacement. So for example, the gravitational force is a big one. It's pulling down on you, but you're not being displaced in the y direction. So that force is not doing any work. Uh, in fact, sometimes if you have something that is moving, so for example, if I have this and it's moving left to right, there are forces acting on it. There are lots of forces, right? I have a force that's pushing it in this direction, causing it to move in this direction. And in that case, that force is doing work, but there's also the gravitational force, which is not causing any displacement, and so that force is not doing any work. So when we talk about work, we'll talk about different forces that do work on the object, but we'll see that those different forces do different work. So sometimes a force will do work, and sometimes a force will not do work. So you have a picture here. So here, for example, I have you just have a bucket that you carry around at a constant velocity. And in this case, you are exerting a force to balance that by gravity, but you're doing no work here. So my force is in this direction, but my displacement is in this direction. And so the work here would be F d cosine theta, or your F times d times the cosine of 90, and that's equal to 0. Let's sort of do a quick little trig check. Okay, so we know that our cosine of 0 degrees is equal to 1. Cosine of 90 degrees is equal to 0. What is the cosine of 180 degrees equal to? That's -1, right? And then likewise, our cosine of 270 is equal to 0. And this comes about on our coordinate x on our coordinate system. Our plus x cosine is equal to 1, 0, -1, 0. So it's like that component along those axes, if you want to think of it in that way. Uh, that's important because when we talk about dissipative forces like friction also do work, but they generally do what kind of work? They generally do positive or negative work. Now think about the direction of a dissipative force like friction, and then think about the direction of the displacement. In the case of friction, if the frictional force is in this direction, what is typically the direction of the displacement? The same direction or the opposite direction? Right. Frictional forces almost always oppose the direction of motion. And since they oppose the direction of motion, the angle between the force and the displacement will be 180 degrees. And so that means that they're going to do negative work because the displacement and force are in opposite directions. All right, let's do this little quick test problem. Um, you try this on your own. The first thing you want to do is just determine the amount of work that's done here. Um, I want to take the dot product of F and D. Notice that I give you initial positions and final positions. So if you want to know the actual displacement, you'll need to take the difference in those two. Determine the amount of work. Power is something that we'll get to later. Power is just the rate at which you do work or work over time. So you can do that. And then try those others as well. All right, so I'll give you a few minutes, a little head start. So how much work has been done by the force? Just go ahead and do that dot product, making sure that you're using the actual displacement, not the initial or the final. Determine the power that's done. And then think about how would you find the mass of the particle. what is my displacement for this particle? I have the displacement for it. What's the displacement? Oh, displacement. Was it Lazarus? That's right. Yeah. So I do 3.25 minus 0.25, so that's going to be 3i. I do 4.5 minus zero point 0.5 plus 4j. And so I can make quick work of that dot product. What's it going to be? 9 plus 6, 25. Right. So I just do 9 plus 16. So that's equal to 25 unit. I'm sorry, Brett, you said joules, right? So I have 25 joules. That's the amount of work that's being done by this force. I want to know the amount of power that's being done as well. What's the rate of power? 12 and a half, right. So my power, we'll define this later, but it's just work over time, and it's 12.5, or actually 13 to be correct with sig figs. Uh, what is the unit of power, does anybody know? What? Watts, yes. Okay, it's watts. Gotta get that. That was a little joke. Watts is the unit for power. It's watt. It wasn't a question, it was a statement. Okay, so that's my power. Let's see, these third and fourth parts are a little trickier. I want to know the mass of the particle. You could find the mass in a couple different ways, but here I gave a little hint that x is equal to 1/2 ax t squared. I know that my x displacement is equal to 3 meters, right? That's this value. That's just my x displacement. My y displacement, by the way, is 4 meters. Um, and I know the time that it occurs in, so I can say that 3 meters equals 1/2 ax times 2 seconds squared. So ax is equal to 3/2 meters per second squared. Oh shoot, how's that going to help me find the mass? If I know the acceleration in the x direction, how can I find the mass? Right, I know also the force in the x direction. So I have to be careful. I'm just dealing with the x components. You could do a similar thing with the y components, but I'm just dealing with the x components. Fx was 3 newtons equals to m times 3/2 meters per second squared. And then I just solve that for m. So it's going to be 3 times 2/3, or 2 kilograms. And then what is the magnitude of the final velocity for the particle? Um, oh, so I know the force is up here. She asked, how do I get the force as 3 newtons? I'm not actually looking for the total force. I'm looking for the x component of the force. So remember, guys, whenever we're working with forces in vector notation, I can split them up and only deal with the x components and only deal with the y components. And I have fx, and I have ax, I found right here, and I have t, I have ax right there, so I can find the mass. So I'm just equating or relating fx and ax. Does that answer your question? Okay. You could do a similar thing with Fy. That would also be true. And then in part D, I'm going to go ahead and show you this. We haven't gotten to this yet, but let me go ahead and show you because it'll come up soon, probably next class period. My work being done here was, what was it, 25 joules? The work being done is 25 joules. We're going to see next class period that the work is equal to a change in kinetic energy, or a change in energy, to be more specific, to be less specific. my work is equal to a change in energy. So any work that I do in this object will change its energy. So 25 joules will cause a change in energy. And we're going to see that our kinetic energy is equal to 1/2 m times v squared. So if I know that this work is changing the kinetic energy of this object, which it is, then I can find its final velocity pretty easily. I can just say v is equal to 2 times 25 divided by m, which is 2 kilograms, square root of that. So that's equal to 5 meters per second. Don't sweat that right now. We'll see that next class period. We'll get to it. All right, let's do some clicker questions. If you don't follow this right now, that's okay. There's a few homework problems to help you along with this. So, but that is a good example of a test question that you might see. Oh shoot, I had the answers here. I'm sorry, but we will do some more clicker questions in just a second. Y'all remember Dr. Baker? Y'all never had Dr. Baker, did you? Y'all ever heard of him? Did you have? Oh, he was a great guy. Right? Sometimes students didn't really like him. You probably liked him, didn't you? They were tough, yeah. But he's a likable guy. Uh, he was a lot more likable after he got married, actually. I don't know why, but he was just, I don't know. Vicky Baker, did y'all know her? She was in math. She was just a really great person. But anyway, uh, one time, this is sort of related to this. One time he gave a test in his class, and it was his practice when he was making out the test to bold all the answers so that he could go back and he'd work through the test himself and sort of check, make sure they got the answers right and all that. It's all right practice. But one day he printed the test and gave it to his students, and guess what? They were all bolded. All the correct answers were bolded. Like every correct answer was in bold. And the students got it, and you know what? Like they didn't do very well on the test. I guess they thought he was trying to trick them or something, or maybe they just didn't notice that all the correct answers were bolded. But anyway, the correct answers are here. Um, the force, I have these four objects. They each have a force of the same magnitude, and they're all moving to the left. All right, so there are some other forces acting on these, but in particular asking which of these forces do no work. This one does no work because it's perpendicular. The one that does negative work is this one, right? It does no negative work. Why? Why? It's opposite the direction of motion. That cosine theta term, theta is 180. Theta equals 180 here. All right, you can think of it as just opposite the motion. The forces that do positive work are this force, because it's in the same direction as the motion, and this force, but only a certain component of this force, only the x component of that force does work. And the force that does the most work is B. That's not entirely true, actually. What other force does a similar amount of work? C also does the exact same amount of work, but it's negative. Now, work is what type of quantity? A vector or a scalar quantity? It's a scalar quantity. So you're probably thinking, well, shoot, he just said that that force does negative work, but I also said that work is a scalar quantity. What gives, right? Because usually in the past, all semester, we've used negatives to denote direction. But in this case, with work, we're not going to use a negative to denote direction. We're going to use a negative to denote like giving and taking away. So we'll let a positive work mean that we're giving energy, and a negative work mean that we're taking away energy. We'll see that again next time, but I just want to introduce it here. Let's do a few clicker questions. Are you finding this a little easier than chapter 4? This is really the meat of the chapter. We have a few more topics to present, but it won't get much more complicated than this. Okay, is it possible to do work on an object that remains at rest? Is that possible? Think about what work is, how to find it. All right, I'll stop at 30 seconds, 30. Okay, the answer here is no. Why is it no? What is the work? It's the force times what? Displacement. And if an object is at rest, what's its displacement? Zero. So the answer is no, because the displacement is zero. Box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? Does it do no work, negative work, or positive work? All right, I'll stop at 33, 33. All right, very good. It does do negative work. If I have my object, it's traveling in this direction. That's my displacement. But the frictional force, Fk, is in that direction. So the angle between them is 180. That work is negative. Uh, and remember, that doesn't denote a direction of the work because work is not a vector. It denotes something else. It means basically that it's negative, means that it's slowing the object down, which is almost always true for friction. Can friction ever do positive work? The answer for this is yes. All right, so go ahead and just click in yes. I'll show you why. Imagine that you have a truck, like a flatbed truck, and you have an object on the back of it. Now, in this case, the truck is moving in this direction. So the displacement is in this direction. What is the direction of the frictional force that's acting on the block? It's in the same direction. So think about my frictional force, Fs in this case, is in that direction. It's a good thing too, right? Because if there was no frictional force, the object would just go off the back of the truck. So in this case, we do have a frictional force that's in the same direction as the displacement. That's not usually true for frictional forces or dissipative forces in general, because usually they take energy away from the object. But in this case, the frictional force is actually imparting energy to the object. So the answer here is yes. I'll stop at 110. Awesome. In a baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? Has the catcher done positive work, negative work, or zero work? The catcher exerts a force on the ball. Think about that force. Does it do positive, negative, or zero work? Stop at 40. Stop at 40. Okay, B is right. Listen, we'll get this a little bit later when we see how work is related to energy. Uh, but when you slow down something, that means that you're doing negative work. Or you can think about it in this way, that I have this ball that's coming in this direction towards me. So the displacement of the ball is in this direction, but the force that the catcher exerts is in this direction, right? Because the catcher with his glove imparts a force to the ball that's opposite the direction of its motion. So that's going to be negative work. B is the right answer. Or I like to think of it as it's slowing the object down. That means it's taking away energy. That means it has negative work. But again, we'll get into that next time. You can think about it in this terms of F and D as well. Okay, why don't we stop there? Um, I want you to take out a sheet of paper. I feel like, you'll do assessments at the end of the semester, but I want you to just write on a sheet of paper, a blank sheet of paper with no name on it, So anonymous, but just write one thing that you like about the course and one thing that you'd like to change about the course. You'll do assessments at the end of the semester, and that's great for future students. But like if there's something you'd like to change about the course mid-course, midstream, then we'll certainly consider it. It looks like Brett has paper for everyone. All right. So one thing that you like and one thing that you'd change about the course, just write on a sheet of paper. You can go when you're done. You can just set it here. One thing that you like and one thing that you would change about the course.